Hi, I'm Shaohong. Today I'm going to introduce our work, Thunderbolt, throughput-optimized, quality-of-service-aware power capping at scale. Let's start with the motivation. What are power oversubscription and power capping, and why do they matter? Data centers are expensive. In 2019, more than $200 billion are spent on data centers. So it's highly desirable to fit as much capacity as possible in every data center. Power oversubscription is an effective way to do so. Very often, power is the limiting resource in a data center, but the data center's aggregated power usage is rarely close to the theoretical maximum because the power usage of the many machines in a data center is unlikely to peak at the same time. Therefore, we can deploy more machines in a data center than the power supply can nominally support. This is called power oversubscription. However, power spikes are rare, but they are not impossible. So we need a protective system to avoid overloading the power equipment due to rare power spikes. Power capping is such a protective system. It shaves power spikes by throttling tasks running in a data center. But it has to do so without violating the task's service level objectives or SLOs. How can we do throttling without violating SLOs? We have to respect the task's different quality of service. Broadly speaking, there are two types of tasks, throughput-oriented and latency-sensitive. Throughput-oriented tasks only need to complete on the order of hours or more. Examples are web indexing and log processing. They are amenable to performance throttling because they run slower, but that's okay as long as they can still complete in time. They're not amenable to disruption because it wastes work and may potentially violate throughput SLOs. Latency-sensitive tasks are different. They respond to requests on the order of milliseconds to seconds. Examples are web front-end and search service. They are not amenable to performance throttling because they may become unresponsive. In our data centers, tasks of the two types are co-located on the same machines. It's because our cluster scheduler does not assign priority or QoS to machines. They are assigned to tasks. This improves machine utilization, but it also gives us a big challenge. So our goal is a task QoS-aware power capping system that gently throttles throughput-oriented tasks and exempts latency-sensitive tasks. Existing industry solutions did not meet our needs. It's because they are either task QoS-aware but has disruptive capping action, or have gentle throttling but coarser-grained QoS differentiation. They are appropriate for certain scenarios, but they do not meet our needs. So we developed our own system, Thunderbolt. It simultaneously achieves the following goals: power safety with minimized performance degradation, task-level QoS differentiation, hardware platform independence, and tolerance of power telemetry unavailability. All of these are important to scale out our mission-critical system. We have deployed Thunderbolt at scale in Google data centers over the years and enable oversubscription of 9 to 25% in our logs processing clusters where none was previously possible. Let's look at the architecture and implementation of Thunderbolt. Thunderbolt has two subsystems: a reactive capping primary subsystem that operates when power signals are available, and a proactive capping failover subsystem that operates when power signals are unavailable. Let's go through them one after another. Reactive capping operates when power signals are available. The meter watcher module here reads power readings from the data center power meters and passes the readings to the power notifier module. At the same time, it also stores a copy of the readings in the power history data store. The power notifier module compares the power readings to the power limit it gets from the power topology data and uses the load shaping policy that we will introduce later to make throttling decisions. It passes the throttling decisions to the machine manager module, which sends throttling RPCs concurrently to the distributed node controllers. Finally, the node controllers throttle tasks using a CPU bandwidth control mechanism that we'll introduce later. Proactive capping operates when power signals are unavailable. When that happens, the risk assessor module reads the power history from the data store and assesses the risk of power reaching power limits. Then it passes the results of the risk assessment to the power notifier module, which will make throttling decisions based on that. Then the rest is similar to reactive capping, except that the node controllers will throttle tasks using a different mechanism, CPU jailing, that we will also introduce later. Next, let's look deeper into the mechanisms and policies of reactive capping and proactive capping. Reactive capping uses a node mechanism called CPU bandwidth control. It's a Linux kernel feature, so it's purely software and is platform independent. It's capable of setting task-level CPU cap. In particular, each task is assigned to a control group or a C group, and a CPU cap is assigned to each C group by setting its quota parameter. Let's look at an example here. In this example machine, a period parameter is set to 100 milliseconds. There are two tasks, one assigned to a C group with 70 milliseconds of quota, and the other assigned to another C group with 90 milliseconds of quota. So task 1 here will have up to 70 milliseconds access to the CPU every 100 milliseconds, and similar to task 2. If the machine has two logical CPUs, then its CPU utilization is capped at 80%, which is equal to the sum of the quota of all the tasks divided by the sum of the period of all the logical CPUs. Why do we choose CPU bandwidth control rather than other popular power management knobs like RAPL or DVFS? Although RAPL and DVFS have their own merits, we don't use them because of their limitations. RAPL is per-socket control, so it cannot achieve task-level control without additional scheduling constraint. It's Intel-specific, so it's not desirable for our clusters with diverse platforms. Although it has the merit of precise power control and wide control dynamic range, it doesn't meet our needs. DVFS is supported by most modern platforms, but its per-core control is not. For example, it's not supported by Intel pre-Haswell microarchitectures and some non-x86 platforms. It has narrower power control dynamic range than CPU bandwidth control. However, it does have the merit of higher throughput than bandwidth control under the same power budget. We decided that CPU bandwidth control's native task-level control and platform independence is vital for scaling out our system, although DVFS may be added for future efficiency optimization where per-core control is supported. We have tested the three mechanisms on a Intel Skylake CPU. On the left, we run a power virus workload and plot normalized CPU power versus normalized set point of the three mechanisms. We can see that RAPL has the widest power dynamic range. Bandwidth control also has a fairly wide power dynamic range, but DVFS has a quite limited dynamic range. On the right, we run video transcoding workload, which is throughput-oriented, and plot normalized throughput versus normalized CPU power. From the CPU power, we can see that in this test, bandwidth control also has wider power dynamic range than DVFS. Given a power budget, however, DVFS has better throughput than bandwidth control. Therefore, we may use it for future efficiency optimization. Reactive capping uses a control policy called load shaping. Load shaping is a combination of a randomized unthrottling multiplicative decrease algorithm and a two-threshold with two multipliers scheme. Randomized unthrottling means that we unthrottle machines randomly over time when throttling ends. Multiplicative decrease means that task CPU cap decreases multiplicatively when throttling is active. And we use a two thresholds with two multipliers scheme to balance safety and efficiency. We achieve QoS differentiation by exempting latency-sensitive tasks. It's important to note that we have continuous monitoring to ensure power safety with the exempt tasks. That is, the exempt tasks will not draw too much power, and by throttling only the throughput-oriented tasks, it's sufficient to reduce enough power. Let's illustrate it with an example. At the top here, we show a power time series aggregated over many machines and tasks. At the bottom is the CPU quota and CPU usage of a particular throughput-oriented task. In the beginning, the low threshold is not activated, so power can go above the low threshold without throttling. Suppose it keeps increasing and hits the high threshold. Then two things happen. The low threshold is activated, and we start hard throttling. Hard throttling works by applying a hard multiplier close to 0, say 0.01, to the CPU usage in order to quickly reduce power. In this example, we apply 0.01 to 200 and get a 2 milliseconds of quota, so the task can use only up to 2 milliseconds of the CPU in the next time step. As a result, power will reduce. Suppose it reduces below the low threshold, then we start to unthrottle. We do that by unthrottling machines randomly over time, so power can gradually go back up. Then power goes back up and hits the low threshold. Then we start soft throttling by applying another soft multiplier close to 1, say 0.8, to the CPU usage in order to gently throttle the tasks. So we apply 0.8 here to 100 to get an 80 milliseconds of quota. Suppose power stays above the low threshold because the throttling is not hard enough. Then we will continuously apply the soft multiplier to the previous usage to get the new quota. We can see that by continuously applying the soft multiplier, we guarantee that the CPU usage of the throughput-oriented tasks will keep decreasing. So power will eventually decrease below the low threshold. Then after a certain period of time without throttling, the low threshold will expire, allowing power to go into the region between the two thresholds. So we make more efficient use of the power budget. We have tested load shaping on a production cluster that has tens of thousands of machines and runs diverse workloads, including both throughput-oriented and latency-sensitive. We can see clearly the sawtooth-like pattern of power oscillating around the threshold. We can also see that power is reduced very quickly in 2 seconds after throttling starts. We can also see that a smaller multiplier leads to power oscillation with greater magnitude. We also look at task failures and latency of latency-sensitive tasks. And we see that low shaping has negligible effect on task failures and latency. Then let's turn to proactive capping. Proactive capping uses a known mechanism called CPU jailing. CPU jailing sets deterministic machine CPU cap, which is important for power safety when we don't have power signals. In particular, we set a jailing fraction parameter, or J, and this fraction of logical CPUs on each machine are made unavailable to all the tasks. As a result, each machine's CPU utilization is capped at 1 minus J. In this example, a machine has 10 logical CPUs, and we apply a 20% CPU jailing, that is J equal to 0.2. Then 2 logical CPUs will be made inaccessible to the tasks. We can determine J by translating a power budget to a CPU budget using a model of power-CPU relation. One disadvantage of CPU jailing as compared to CPU bandwidth control is its relaxed QoS differentiation. That's because the jailed CPUs are inaccessible to all the tasks, including latency-sensitive ones. This is required for strong power guarantee even without power signals. Nevertheless, the higher priority latency-sensitive tasks still have more access to the remaining CPUs, so we still achieve relaxed QoS differentiation. We have also tested 20% CPU jailing on the same production cluster that we test low shaping. We see that CPU jailing also has negligible effect on task failures and latency. Proactive capping uses a control policy of risk assessment. When power signals are unavailable, we use a probabilistic model to assess the risk of power reaching power limit based on the power of the recent past and the duration of meter unavailability. If the risk is high, then we will start CPU jailing, otherwise we don't jail. We use a conservative model that has low false negative rate. The details of this model are out of scope for confidentiality, but any conservative model that assesses risk and makes a binary decision can be used here. We have deployed Thunderbolt at scale in our logs processing clusters. The workloads in those clusters are mostly throughput-oriented, but there are also critical latency-sensitive tasks, so the task QoS-aware awareness is important. As a result, we have enabled 9 to 25% power oversubscription. And in production, throttling has triggered 5 times in 5 clusters in the first 130 days in 2020 with negligible performance impact. In summary, power oversubscription with power capping is an effective way to reduce data center costs, but the throttling needs to be compatible with SLOs. We have developed Thunderbolt power capping system that achieves power safety with minimized performance degradation, task-level QoS differentiation, hardware platform independence, tolerance of power telemetry unavailability. We have deployed Thunderbolt at scale in our logs processing clusters over the years and enabled 9 to 25% oversubscription. The system has triggered in production with negligible performance degradation. Thank you.